All right, let's talk about one of the most powerful, most incredible pieces of tech you can actually own, the graphics card. I mean, this thing is the beast that powers everything from games that look more real than reality to the AI that is literally changing our world. So how on earth does it actually work? Let's get into it. First up, I've got a question for you. When you're running a game that's just jaw-droppingly beautiful, something like Cyberpunk 2077, how many calculations, how many little bits of math do you think your graphics card is cranking through every single second? The answer is absolutely insane. It's 36 trillion. Now, a number that big is almost meaningless, right? So let's try to wrap our heads around it. Imagine every single person on this planet, all 8 billion of us, doing one calculation every second. To match what one high-end graphics card is doing, you would need, get this, 4,400 Earths, all filled with people calculating at the same time. That is the kind of power we are talking about, sitting right there in your computer. And you can really see just how far we've come with this timeline. You know, back in '96, the legendary Mario 64 needed about 100 million calculations a second, which was a huge deal then. Fast forward to 2011, and a game like Minecraft is hitting 100 times billion. And now, we've just skyrocketed to 36 trillion. It's this crazy exponential demand that has forced GPUs to become the powerhouses they are today.
So what's the magic trick here? What makes a graphics card, and specifically its brain, the GPU, so completely different from your computer's main processor, the CPU? Well, to get this, we're going to use a really simple but honestly perfect analogy.
Okay, think of your CPU as a jumbo jet. It's blazing fast, it's super flexible, and it's perfect for handling a few really important tasks right now. Your GPU, on the other hand, that's a massive cargo ship. It's not as fast, but its one job is to move an unbelievable amount of stuff all at once. And that's the key difference. A CPU has just a few really powerful cores for all sorts of different complex jobs. A GPU has thousands of simple cores designed to do one kind of simple, repetitive job just on a massive parallel scale.
All right, now let's pop the hood. Let's zoom way, way in and actually look at the physical layout of the GPU itself. We're going to take a little tour of the silicon to see how all these thousands of cores are put together. So this right here is the GA102 chip. It's the heart of a powerful NVIDIA 30 series card. And what you're looking at is an engineering masterpiece with over 28 billion transistors. But they're not just a random jumble, oh no. They are organized in this brilliant, super logical hierarchical structure. It's kind of like a set of Russian nesting dolls. You start with the whole GPU chip. That chip is then broken down into big sections called graphics processing clusters, or GPCs. Inside each of those, you've got smaller units called streaming multiprocessors, or SMs. The work inside those SMs is managed in little groups called warps. And then finally, at the very bottom, you have the individual CUDA cores, the little tiny soldiers actually doing the math.
But here's the cool part. It's not just about how many cores there are, it's that they're specialized. On this chip, most of them, they're CUDA cores. They're the workhorses for gaming. But you also have hundreds of specialized tensor cores built for AI and dozens of ray tracing cores that are designed specifically to calculate how light bounces around a scene. It's like having a whole team of specialists on one tiny chip.
Okay, so this brings up a really good question you might have. If cards like the NVIDIA 3080, the 3080 Ti, and the 3090 are all built around the same GA102 chip, why in the world do they perform so differently and have such wildly different price tags? Well, the answer comes down to the messy, imperfect reality of manufacturing. It's a process called binning. See, when you're making something this complex, tiny specks of dust can cause tiny little defects. So instead of just throwing away a chip that's not perfect, manufacturers test them. The absolutely flawless ones with every single core working perfectly become the top-of-the-line 3090 Ti. A chip with a couple of tiny flaws, they just deactivate those faulty parts and it becomes a 3090. A few more defects, boom, you've got a 3080. It's actually a genius way to get a whole range of products from a single manufacturing line. Okay, so we've seen the hardware, we've got thousands upon thousands of cores all ready to go, but how do they actually work together to get anything done? Well, that brings us to the fundamental concept that makes GPUs so special: parallelism. GPUs are purpose-built to solve a very specific kind of problem, and it has a hilarious name, an embarrassingly parallel problem. All this means is that it's a task that's super easy to break up into thousands or even millions of little, tiny, independent chunks that don't need to talk to each other.
And as it turns out, computer graphics, crypto mining, and AI are just full of these kinds of problems.
And the principle that lets them do this is called SIMD. It stands for Single Instruction, Multiple Data. But the idea is really, really simple. You take one single command, like, say, add these two numbers, and you blast it out to thousands of different pieces of data all at the exact same time. One instruction, thousands of simultaneous results.
Let's make this super concrete. Check out this 3D model of a cowboy hat. It's made up of about 14,000 individual points, or vertices. Now, to put that hat on a character in the game, the GPU has to do the exact same math transformation on every single one of those 14,000 points. See where this is going? It's a perfect SIMD problem.
So the GPU doesn't do this one by one. No way. It takes that one instruction, move this vertex from here to there, and just blast it out to all its cores at once. Now, when you're talking about a full game scene with millions of vertices, just that one step can mean doing over 25 million addition calculations. And because it's an embarrassingly parallel problem, the GPU just crushes them all at pretty much the same time. That's the beautiful brute force power of parallel processing. And here's where things get really wild. This amazing parallel power, it's not just for making games look good. It has completely transformed other fields that also happen to be full of these embarrassingly parallel problems, like crypto and AI.
Let's take Bitcoin mining. At its core, the job is to guess a winning lottery ticket by running a specific algorithm over and over again with different numbers. Since every guess is totally independent of the others, it's another perfect job for a GPU. A single graphics card could try about 95 million different lottery tickets every second just by giving each of its cores a different number to try. Now today, super specialized chips called ASICs do this even better, but GPUs are what started the whole revolution.
And then you have AI. Modern AI is built on a type of math that involves multiplying and adding huge grids of numbers together. And remember the special tensor cores we talked about? This is their moment to shine. They are custom-built calculators for doing exactly that one job. They can take these giant tables of numbers and do all the math at the same time. It's the ultimate cargo ship problem, moving and processing massive amounts of simple data all at once.
So there you have it. From painting a single pixel on your screen to simulating entire world and powering artificial intelligence, the humble graphics card has become this absolute beast of parallel computation. And it just leaves you with one final mind-bending thought. If this is what we can do today, what are the monumental problems we're going to solve when these things are another 100 times more powerful?